The aim of the project was to create a data gathering, evaluation and marketing system for evaporative roof cooling systems for industrial buildings. The roof is the part of the building receiving the largest solar load and the largest surface where heat from within the building could escape. Roof cooling can greatly reduce the overheating and cooling energy demand of industrial buildings. While roof cooling has been demonstrated to work very well, and our company has such a patented system, WaterFilm Technology, decision makers require hard data in advance before adopting such a new solution. The purpose of the project was to quantify the operation of roof cooling systems. The biggest problem with launching this system to the market is that there is no standard sizing method to accurately predict how it will work and how much we will save. Most decision makers prefer making decisions based on a standard calculation method. The Evaroof system is specially designed to solve this exact problem. We have designed monitoring modules that can measure the most relevant physical parameters that determine the operation and impact of roof cooling systems. The cooling system works by spraying a film of water onto the surface, which removes heat from the surface by evaporation. On the one hand, the monitoring modules are designed to monitor this process, for which humidity and temperature sensors above the roof are used, which are able to measure the air conditions at various points of the boundary layer that forms on the roof surface. In addition, we measure the energy flows through the roof, which allows us to determine the energy balance of the entire structure and calculate energy savings.
Energia mérlegét, ami az energetikai megtakarítás szempontjából ugye meghatározó. Erre szolgál a tető.
For this, we use surface temperature sensors on both sides of the roof, as well as a heat flow density sensor. The third major category, the third module type, measures the thermal comfort conditions within the building. The two big advantages of the system are the energy savings and the improvement of the thermal comfort conditions inside the building. With our modules, we can quantify both, as well as gather data that could be used in the future to develop calculation models. The modules transmit every measurement via the internet to our server, where we store them and can easily access them for various purposes. As part of the project, we have first created test prototypes for all types of measuring elements. These are now working here on the building under real conditions. We use these to demonstrate that the system can work in real conditions, on the roof surface in the strongest wind and rain, or when the water sprinkler system is working. Measurements are made in 1-minute intervals, and it takes just a second for data to arrive on the server, so we can do real-time monitoring. Here we can see the data recorded by one of the modules in the last 24 hours. This is the module placed on the roof, which shows the air temperature and relative humidities above the roof. With the Evaroof system, we will be able to conduct scientific tests in this building, survey existing roof cooling installations, and use it for new projects from the preparatory stage on. We will be able to demonstrate the energy savings and the thermal comfort improvements brought by roof cooling installation from direct heat flow and comfort measurements, and not just estimate it from energy bills or subjective testimonials. With warming temperatures, cooling energy demand gains more and more importance, and especially so for industries with large internal heat generation. The Evaroof system, from the monitoring modules to the server, and its ability to publicly share the measurement data and our analysis online, we will gain a quality assurance and marketing tool unlike any other.
Hi, I'm Eduardo Dueñas from Owners Partners. In this project, Evaroof, for Meta Building, we have created a series of prototypes to test this technology. So here I'm going to focus on the hardware part that we have tested here in our facilities where we built them. This prototype here is for the module 1 and 3. The difference between those is that one of them is installed outdoors, in the upper part of the building, in the roof, and then the other type of module is installed inside, indoors, inside the building. So that's the difference, but the hardware itself is mostly the same. So this first module, this first set of modules has what we call the main board, which is inside this box. I'm going to show you later on an example with the other one, with the module number 2. And then we have a slave. What is another sensor which is cabled to the main body, because we can have several slaves. Then we have another external sensor which we have enclosed inside this black sphere, and then we have another example of module number 2, which, for example, you can see here how this board, which is also custom made for us by us, this is what we have installed also inside this other module, another version, but more or less the same implementation. And then we have the same. We have an external sensor. In this case, this is the external sensor for the heat flux, as we can see here. Besides the heat flux, we can also measure surface temperature. It can be done using the same heat flux sensor or an additional sensor, which would be also connected to this board. And then all the measurements that are inside this body, inside this main module, are going to be connected using an Ethernet connection through a switch. So with this switch, which is a power over Ethernet, PoE switch, we can both have the power supply for all the modules and also the communication for all the data transferred between the modules to the server.